All right. Okay, areas under any normal curve. We're going to compute the probability of standardized events, find a z-score from a given normal probability, so inverse normal, and use the inverse normal to solve guarantee problems. Apologize, my phone is blowing up, so I will get rid of it. So let's look at some normal distribution areas. In many applied situations, the original normal curve is not the standard normal curve. Generally, we are not able to use the table, so we have to convert it. Typically, you're given x, a, and b, and then you need to convert it to z values. And as an aside, let me note for you guys. All right. Here's how the procedure works. We are going to find the areas and probabilities for a random variable x that follows a normal distribution with mean mu and standard deviation of sigma. Convert x values to z values using the formula. You can use this either direction. So if you're given a z value, a mu, and a standard deviation, you can solve it to find x, as well as if you're given the three variables on the right side, you can solve it to find z. Once you have your z value, you can then go to table 5 in appendix 2 and find the corresponding areas and probabilities. All right. So let's look at this example. Let x have a normal distribution with mean 10 and a standard deviation of 2. Also, you guys should know that you will always be told if it's a normal distribution. If you don't see the word normal distribution, then you cannot use this approach. Find the probability of an x value selected at random from this distribution between 11 and 14. So if you were given it in simples, this is what it would look like. So we have to find how many z-scores here. Are we only finding one? Are we only looking for one? How many x's are you given?
Is it 2?
It is 2. Okay, so we're going to solve the z-score twice. So we're going to convert and use x equal to 11, mu of 10, and sigma of 2. And then we'll do it again for x equals 14, mu of 10, and sigma of 2. Okay. Once we have these two z-scores, we would then go to the z-table. You could draw it out if you wanted to. Sometimes when you're doing this for the first time around, drawing them out is beneficial because then you can kind of know if what you're looking at in the z table is making sense or not. So here you can see that both of these values would be above 50%. Okay, here when we have a z value of 2, we have a z probability equal to 0.9772. Granted, that is as a z-score, and if you wanted to make it a percentage, you would have to multiply it by 100. So, and then the 0.5 is a z-score of 0.6915. If you looked these two values up in your table, you would find these two values. You subtract them, so the probability of 0.2857 means that an x value randomly selected between 11 and 14 will be about 28.57%. All right. Any questions on this conversion? Okay. All right. Oops. Always do that. All right. Inverse normal distribution. And just so you guys know, I have the chat open as well. So if you feel better answering questions in the chat, go ahead and do that. And it is open so that I can, I won't have to sit here in silence if you answered in the chat. All right, inverse normal distribution. Sometimes we need to find an x or a z or an x value that corresponds to a given area under the normal curve. This situation arises when we want to specify a guarantee period such as that given in a percentage of the total products produced by a company. So basically, if you're told the percentage of something, then we have to kind of work backwards and figure out how much of the items need to be produced in order to guarantee that percentage of production. All right. Now, granted, keep in mind some of these you could have human error. So even if let's say this is your job and your job is in quality control or quality assurance, you could give the manager or the floor foreman the information, but even if you give them the right information, they might turn around and say, well, your information didn't work. The reason for that is going to be human error. Okay. If you have an absolutely completely controlled system, then your math should always be correct. All right. Magic Video Games Inc. sells an expensive video game package. Because the package is so expensive, the company wants to advertise an impressive guarantee for life expectancy of its computer control system. The guarantee policy will refund the full purchase price if the computer fails during the guarantee period. The research department has done tests that show that the mean life for the computer is 30 months with a standard deviation of 4 months. Let me just tell you that as a gamer, there is no way I would buy a computer system that only is going to last me 30 months. That's like what? 2.5 years plus or minus 4 months. I would be told no from the jump. So I don't know really what kind of platform they're trying to sell here, but I would not buy it. I'm sure someone who is not a gamer would maybe think 30 months is great, but I would want to see more like 60 months there. All right. The computer life is normally distributed. How long can the guarantee period be if management does not want to refund the purchase price on more than 7% of Magic video packages? So, the first thing we have to look at is we're going to look at the distribution of lifetimes of the computer control system and shade the portion of the distribution in which the computer lasts fewer months than the guarantee period. So 7% is just what they're willing to pay, or what they kind of want to keep around their payment. That doesn't necessarily mean that 7% is going to be what ends up happening. So anyway, your job is to find them what the X is. So we're going to work backwards here. So you guys basically have the background knowledge just from that information there. So we have to figure out what our Z is. So if you have 7% and we convert it to the decimal, well, that's the area value, and that is what the Z would end up helping you find the Z. So normally you find the Z and you go down and over to find the actual area. Now you're going to find in your table the area closest to 0.0700, and you're going to shoot up and out, and that's going to get you your Z value. So here it says that the area under the table, the closest thing we can get to is 0.0694. So if we shoot over, we get negative 1.4, and we shoot up, we get 8. So our Z-score is negative 1.48. To translate this value back to the X in months, we need to now rearrange that original formula. So here's what you're used to seeing. You're used to seeing Z equals to x minus mu over sigma, right? So all they did is they rearranged it to now have x on the left. Okay. Now that if you wanted to, you could plug it into the original and then rearrange it. Whatever you would decide to do would be obviously your prerogative at that point. So you get about 24.08 months. Obviously, they don't really care about the days. So X is going to be 24 months. For this period, they expect to refund the purchase price of no more than 7% of the video game packages. So basically, every 24 months, they're paying a refund amount for 7% of the video game packages. I don't know. I don't feel like it's a pretty smart system, but it was a decent example, so we'll go with that. All right, here's your procedure. How to determine whether data have a normal distribution. The first thing you want to do is draw your histogram. You can pretty much tell from the histogram if it's going to be bell-shaped or not. The second thing is looking for outliers. So if you have a data point that's above Q3, which you would take 1.5 times the IQR, or below Q1, again 1.5 times the IQR, then you have some outliers. For normal distribution, there should not be more than one outlier. So you can have one outlier, you just can't have many outliers. Number 3 is talking about skewness. Here's this Pearson index, 3 times the X bar minus the median divided by S, which you know is the standard deviation. And then that typically is between 1 or -1. Okay, it helps you determine the skewness. Skewed distributions are not normal. So basically you want a 0 there, or as close to 0 as possible. Normal quartile plot or normal probability plot. I don't really think you have to worry too much about this stuff. Basically just if you will be able to know if it is normal or not. Okay? If you guys work through your homework and you need to help going over some of this stuff, just let me know. We can plan some time outside of class to work over it. All right. Consider the following data, which are rounded to the nearest integer. Okay. So my first statement to you would be probably use Excel and get these all in numerical order. That's what I would do. It says, look at the histogram and box and plot whisker plot generated by Minitab in figure 630 and comment about the normality of the data of these indicators. Note that the histogram is approximately normal and the box and whisker plot shows just one outlier. Both of these graphs indicate normality. At this point, you guys have already tested, right? You guys already tested on the histogram and box and whisker plot. So at this point, you should be able to either do them by hand, or if you have figured out how to do them on Excel. Again, if you guys are interested in knowing how to work the Excel sheets, I always use Google, so I can't help you with regular Excel too much. They're kind of similar, but I just don't have a regular Excel to cast. I can only show you Google Sheets. All right. Use the Pearson index to check for skewness. This is your summary from Minitab, which Minitab is part of Pearson. You're able to just work it straight out that way. We see that X is equal to 19.6. The median is 19.5. This is X bar, by the way. Yep. And then standard deviation is 2.705. So then the index, are you going to work? Thank you. The index is between -1 and 1, so we detect no skewness. The data appear to be symmetric. All right. Look at the normal quartile plot and comment on the normality. The data fall close to a straight line, so the data appear to come from a normal distribution. Again, I don't know how much your homework is going to hit on this stuff, and I don't know how much the exam is going to hit on it, but I believe what happens is that they'll show you stuff like this, and then you have to decide if it's close to a normal distribution or not. All right, interpreting the results. The histogram is roughly bell-shaped. There is one outlier. Pearson index does not indicate skewness, and the points on the normal quartile plot lie fairly close to the straight line. So more than likely, this is a normal distribution. Any questions on this section? All right. Okay. We're going to move on then to sampling distributions. This part should all be a review for you. Random sample, relative frequency, parameter, statistic, and sampling distribution. And then we're going to, from raw data, collect a relative frequency distribution for mean values and compare the result to theoretical sampling distribution. Again, all of that is review of vocab for you. Okay. When we compute a descriptive measure such as an average, it makes a difference whether it is computed from a population or from a sample. We talked about this before a little bit. Remember, a statistic is a numerical descriptive measure of sample, whereas parameter is a numerical descriptive measure for population. And then down at the bottom here, you have this little chart. I would just go ahead, and if you're someone who writes it out, go ahead and do that. Excuse me. I can't really tell you why it's a big deal other than that there's convention, and that's basically where that comes from. So, and then it also helps, like, when you get deeper into the statistics, knowing whether something is coming from a sample versus whether something is coming from a population. All right. Often we do not have access to the measurements of an entire population because of constraints, time, money, or effort, not to mention like legality. So we must use measurements from a sample instead. In such cases, we will use a statistic to make inferences about the corresponding population. Okay. So a lot of this can get confusing if you don't understand the differences between the representations. And remember that sometimes you're even though they stand for the same thing, because one is dealing with a sample and the other is dealing with a population, then we can often think that it's going to repeat, but that is not always the case. Okay. Types of inferences. There's estimation. In this type of inference, we estimate the value of a population parameter. Number 2, for testing. In this type, we formulate a decision about the value of the population parameter. And number 3, regression. In this type of inference, we make predictions or forecasts about the value of a statistical variable. To evaluate the reliability of our inferences, we will need to know the probability distribution for the statistic we are using. That means we need to know the z-score. Question for you. Why do we need to have reliability? Or why as researchers is it important to be able to replicate or have someone else replicate your study and get similar results? Why is that an important thing? So take a step back from taking notes or listening to me babble on and consider for a moment, why is it important from a researching standpoint for you to be able to have your results replicated? Why do you think someone might want that? Okay. Well, you guys can think about that, and I will ask you again on Wednesday. All right. Sampling distribution is a probability distribution of a sample statistic based on all possible simple random samples of the same size from the same population. So let's look at example 11. Pindale, Wisconsin is a rural community with a children's fishing pond. Posted rules state that all fish under 6 inches must be returned to the pond. Only children under 12 years old may fish, and a limit of 5 fish may be kept per day. Susan is a college student who was hired by the community last summer to make sure the rules were obeyed and to see that the children were safe from accidents. The pond contains only rainbow trout and has been well stocked for many years. Each child has no difficulty catching his or her limit of 5 trout. As a project for her biometrics class, Susan kept a record of the lengths to the nearest inch of all the trout caught last summer. Hundreds of children visited the pond and caught their limit of 5 trout. So Susan has a lot of data. To make table 6-9, Susan selected 100 children at random and listed the lengths of each of the 5 trout caught by the children in the sample. So she literally has a table of 500 trout. Okay. All right. So obviously, you would not want to do this by hand. Then for each child, she listed the mean length of the 5 trout that the children caught. Now let us turn our attention to the following question. What is the average length of a trout taken from the Pinedale Children's Pond last summer? Okay. So the solution says we can get an idea of the average length by looking at the far right column of table 6-9. But just looking at the 100 of values does not tell us much. Okay. So let's just take a look. So here's our far right column. If we really wanted to, since it is only 100 means, all right, not 500, we could plug this into Excel, have Excel add it up, and divide it by 100. All right. All right, let's organize our X bar values into a frequency table. We used a class width of 0.38 to make table 610. So here's their 9 classes. Here is their lower and upper limits. Here are their frequencies, and here are their relative frequencies. At this point, you should all be able to compile this. Okay? Note, earlier it had been dictated with a width of 0.4. However, this choice results in the 10th class being beyond the data. Consequently, we shortened the class width slightly and also started the first class with a slightly smaller value than the smallest data value. The far right table of 610 contains the relative frequencies f over 100. Okay, frequencies over 100. This, by the way, just kind of shows convention. If you would have left it at 10, you really wouldn't find the answer incorrectly. It's just a little bit nicer the way they chose to change it up. We know that relative frequencies may be thought of as probabilities, so we effectively have a probability distribution. Because X bar represents the mean length of trout based on the samples of 5 trout caught by each child, we estimate the probability of X bar falling into each class by using relative frequencies. Okay, so here is your normal distribution. How do we know that's normal? They didn't tell us it was normal. Why do you think I can call it normal? I jump to that conclusion. How can I say with certainty that we are looking at a normal distribution here?
Is it because it's symmetrical, or what's the word?
Symmetrical is good. Yeah, it's showing a bell curve, right? So
Yeah.
if we really wanted to, we could take it through all the steps that we just talked about in the last section, but we don't need to, because as far as I'm concerned, once you see this kind of shape, you're good to go. Unless the question were to ask you to break it down, that's good enough for me. All right. The bell-shaped curve represents the theoretical probability distribution that would be obtained if the number of children were much larger. Figure 632 represents a probability sampling distribution for the sample mean of trout lengths based on the random samples of size 5. We see that the distribution is mound-shaped and even somewhat bell-shaped. Okay. Irregularities are due to the small number of samples used over only 100 sample means and the rather small sample size, 5 trout per child. So, before, when we looked at the table, we literally were all worrying that it was going to be 500 data points. And this is basically telling us that that is too small of a sample. Because we used 5 per child and then we figured out those means, they're pretty much saying that 100 is too small of a sample. I mean, I guess it would depend on what you're talking about, but that's how they feel about this. These irregularities would become less obvious and even disappear if the sample of children had been much larger. If we used a larger number of classes and if the number of trout in each sample became larger. In fact, the curve would eventually become a perfect bell-shaped curve. We will discuss this property at some point in length in the next section, which we introduce central limit theorem. Okay. Here's another interesting side bit for you. Okay. Right. At Penn State, you know, there are obviously classes with many students. And when I was there and I took psych, I believe it was like 101. The interesting part was that I had been going to a Penn State campus for 2 years, and then I wanted to transfer up to the main campus. So I switched my section up there. And for some reason, even though I was a junior, I had to take a freshman level course because it was required for your psych degree up at Maine, but it wasn't required on any of the branch campuses because it basically was a waste of a class. But it was so large that I'm pretty sure I had it with like 300 other students. It was disgustingly big. we had to have it in like a large arena style lecture hall. I can tell you that the professor did not know me from Adam, and it was just insanely ridiculous. Um, so we um we didn't know anyone. We just kind of sat there and it was what it was. But what's interesting is that my bell curve for your class would obviously be skewed, right? So like I try not to fail my students even when it is really hard and I can't be nearly as entertaining in person as I could be as I am. I am much more entertaining in person than I am on the computer, even though I literally am trying my best. Um so regard, right? Okay. The central limit theorem. This is probably where your homework is going to get a bit hard and probably the section that will give you the hardest time on the quiz as well. So I extremely recommend that you work those homework problems over and over and over again. I believe there's no cap on how many times you can work the homework problems. The quiz, I believe it's a cap of 5, and the exam is a cap of 3. If for some reason you guys feel like you need a little bit more attempts with that, let me know and I can go ahead and give you some more attempts. Okay. All right. So go ahead and read through your focus points. Well, hopefully Enya can sign back on. All right. Um, for a normal distribution, you use mu and sigma to construct the theoretical sampling distribution for the statistic x bar. For larger samples, use sample estimates to construct a good approximate sampling distribution for the statistic. Learn the statement and underlying meaning of the central limit theorem well enough to explain it to a friend who is intelligent, but unfortunately doesn't know much about statistics. Guess that's a nice way of saying that your friends might not all be smart. The x bar distribution given x is normal. In section 6.4, we began a study of the distribution of x bar values, where x bar was the sample mean length of 5 trout caught by children at the Pinedale Children's Fishing Pond. Let's consider the examples again in the light of a very important theorem of mathematical statistics. Suppose a team of biologists has been studying the Pinedale Children's Fishing Pond. Let x represent the length of a single trout taken at random from the pond. This group of biologists has determined that x has a normal distribution with mean equal to 10.2 inches and standard deviation equal to 1.4 inches. What is the probability that a single trout taken at random from the pond is between 8 and 12 inches long? Knowing what we talked about at the beginning of class in section 6.3, how many z-scores do you need here? I guess before we ask that question, what are you being given here? So obviously you know you have a mean and a standard deviation. What else do you have? What else are you being given? Hmm?
You're also being given that the trout has to be between 8 and 12 inches.
Right. So are those my X's or are those my Z's?
The X's.
Very good. Okay. So because we're being given two X's, because we're given two X's, then we have to find two Z scores. Okay. And at this point, right? At this point, you guys should be able to figure it out from here. I don't know why they're going to take so long to explain this, but I thought they would have more going on here. So you would put one in for 8 and you'd put the other one in for 12. I guess we can watch them do it in slow-mo. Okay. So therefore, the probability is about 0.8433 that a single trout taken at random is between 8 and 12 inches long. Okay. Questions on where they found all of this? Now, if you go through and you're working on your homework and for some reason you keep working on it and let's say you do the practice ones and you're off by 400ths of a point or 4,000ths of a point, so 0.0004, email me and I will get on Zoom with you and we can look at what yours is. And if you are that close, I am just going to give it to you because I'm not sure, even whenever I'm working through some of these, Tucker can contest to it. We followed all of the steps, we did all of the rules, and we were that close, but we were off. So I don't know if they're rounding at a different point. I don't know if they are using a slightly different Z-score table. You should be able to Google them or use the one from your textbook, definitely, and we should be getting the same amounts. So if that happens, please reach out to me so we can take a look at them together and I can decide if I can go ahead and just give you the points for it. All right.
What I've found for the most part is if you round the number, basically round every single number you get to the closest 2 decimal points, that seems to be what they're doing.
Okay.
So I think the biggest one is when you take the square root of the numbers, if you round that and use that rounded number, that'll give you that result.
Good. All right. But it is nice to know that following the steps, even if you follow the steps, if you don't figure out how they want it rounded, you can still end up with the wrong answer. So what I care about is that you're doing the steps correctly. So even if I need to override some of your homework or override your quizzes or exams, I will do so as long as you can show me that you followed the right steps. But definitely take Tucker's advice and go ahead and make sure that if you're doing a square root that you're rounding it to 2 decimal places. And I will do so as well. Okay. So, what is the probability that the mean X bar length of 5 trout taken at random is between 8 and 12 inches? Okay, so if we let the mu of X bar represent the mean of the distribution, then theorem 6.1 part B tells us the following. The mean of the X bar is equal to the mean, which is equal to 10.2. If sigma of X bar represents the standard deviation of the distribution, then theorem 6.1 part C tells us that it is equal to the given sigma, which is 1.4, divided by the square root of n, which in this case would be the square root of 5. And here again, note, just like Tucker told us, they're taking a square root, so they're rounding to only 2 decimal places. Now, if we do it in our calculators, we would actually get a much larger or much longer decimal. So it does look like rounding to 2 places is what the textbook is doing. Okay. Here it says to create a standard z variable from x bar, we subtract the mu and divide by the sigma in relation to x bar. So here they've put everything in. This is basically standardizing the interval. And we're going to use 8 and 10, but here instead of x, we're replacing it with x bar. So we have two different z-scores now. All right? I thought they needed fill-ins. So now we have a brand new probability, which is saying the probability is 0.9977 that the mean length based on the sample size of 5 is between 8 and 12 inches. Okay, so that is a pretty significant jump from what the information we had before. All right, any questions on this central limit theorem? I'm assuming at some point they're going to actually write it out for you. If not, I will screencast it from the textbook. I'll just have to find it. Looking at the results of parts A and B, we see that the probabilities 0.8433 and 0.9977 are quite different. Why is this the case? Well, it literally told us we had to do what? What did we do between the first set of answers and the second set of answers? What did we do? It starts with an S. All right, it starts with an S and it's on this page.
Subtract.
Yes, we needed to subtract, but more importantly, we needed to standardize the interval, okay? So here it says, why is there a difference? Well, according to theorem 6.1, which theorem 6.1 is your central limit theorem. Both x and x bar have a normal distribution and both have the same mean of 10.2 inches. The difference is that the standard deviation, x and x bar, the standard deviation for the x distribution is the sigma equal to 1.4. But then when we replace it with our sigma related to the x bar, we get a standard deviation of only 0.63. The standard deviation of the x bar distribution is less than half the standard deviation of the x distribution. Okay, so do we see why they did that? If you look at the histogram or the curve in part A, look at how much closer it is to the normal distribution in part B. Okay, so basically the same numbering, but here we pretty much found a different sigma and we took into consideration the sample size and we have a much nicer bell curve. Okay. And that is the reason for why you learn how to do this. All right. Looking at the two figures, we see both curves use the same scale on the horizontal axis. This means that the means are the same and the shaded area is above the interval from 8 to 12 on each graph. It becomes clear that the smaller standard deviation for the distribution has the effect of gathering together much more of the total probability into the region over its mean. Therefore, the region from 8 to 12 has a much higher probability for the x-bar distribution. The standard error is the standard deviation of a sampling distribution. So for the x-bar sampling distribution, the standard error is literally equal to that sigma related to X bar. So for the one we just did, it would be 0.63. All right. We are nearly finished, I believe. Yes. Okay. You guys will be able to ask questions before we disembark. All right. The X bar distribution given X follows any distribution. All right. Using the central limit theorem to convert X bar distribution to standard normal distribution, this is what you need to remember. So I would suggest writing it down. Apologies. Did not mean to move it. Okay. So we have to remember that the mean with relation to X bar is equal to the mean that's given. Right? All right. The standard, or sorry, the distribution sigma is equal to sigma divided by the square root of n. And then look, even your z-score is kind of changed up. Because now we're doing it from the relation of X bar, so that kind of changes things. Where n is the sample size, here is a very important part. If n is less than 30, you cannot do this. All right, you have to just use your regular z-score, and it is what it is. And so if it doesn't tell you that have a normal distribution, then you're not going to be able to normalize it. Mean is the mean of the X distribution, and sigma is the standard deviation of the X distribution. Okay, so there you go. All right. Central limit theorem. Here's another example. A certain strain of bacteria occurs in all raw milk. Let X be the milliliter of milk. The health department has found that if the milk is not contaminated, then X has a distribution that is more or less mound-shaped and symmetrical. The mean of the distribution is mu 2500 and the standard deviation is sigma 300 in a large commercial dairy. The health inspector takes 42 random samples of the milk produced each day. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain the sample mean bacteria count, which is X bar. Assuming the milk is not contaminated, what is the distribution of X bar? The sample size is n equal to 42. Since this value exceeds 30, the central limit theorem applies, and we know that X bar will be approximately normal when the mean and standard deviation are the following. Okay. Any questions on how they found the mean related to the X bar and the sigma related to the X bar? Do we all understand how to find that? Okay. Assuming that milk is not contaminated, what is the probability that the average bacteria count X bar for one day is between 2350 and 2650 bacteria per milliliter? So the first thing you have to do is you have to convert this. All right. So we have to find our z-scores related to this X bar normalization or standardizing before we can plug it in. Okay. All right. So X bar given as 2350 converts to a z-score of negative 3.24. 2650 relates to a z-score of 3.24. So you're looking at 0.9994 minus 0.006, which means that the probability that the X bar is between 2350 and 2650 is 0.9988. All right. Again, we can see that that has a much higher probability. All right, interpretation. At the end of each day, the inspector must decide to accept or reject the accumulated milk that has been held in cold storage awaiting shipment. Suppose the 42 samples taken by the inspector have a mean count that is not between 2350 and 2650. If you were the inspector, what would you comment on the situation? Okay. So the probability is that the probability for X bar between 2350 and 2650 that is not contaminated is very high. If the inspector finds the average bacteria count for 42 samples is not between 2350 and 2650, then it is reasonable to conclude that there is something wrong with the milk. If X bar is less than 2350, you might suspect that someone added chemicals to the milk to artificially reduce the bacteria count. If X bar is above 2650, you might suspect some other kind of biologic contamination. Go ahead and write down the procedure and or screenshot it, come back to it later, whatever it is that you guys typically do for that. I will go ahead and read it out to you. So how to find probabilities regarding X bar, given a probability distribution of X values where n is equal to sample size, mean is the mean of the X distribution, standard deviation is the X distribution. If the X distribution is normalized, then the X bar distribution is normal. Even if the X distribution is not normal and we have a sample size of n greater than or equal to 30, then by the central limit theorem, we can have an approximately normal situation. We have to convert for the z-scores and using normal distribution to find corresponding probabilities. All right. That is central limit theorem in a nutshell. I'm going to stop.